I am going to introduce the concept of divergence of a vector field and also determine Gauss's law in point form. Now, in order for divergence not to be just some abstract mathematical operation, we are going to want to keep in mind Gauss's law in integral form. And this would be a good time for you to go back and review the videos Faraday and electric flux and Gauss's law. Gauss's law in integral form is the integral of d dot ds over a closed surface is equal to the charge enclosed by that surface. So d is the electric flux density field, so the integral of d dot ds over this closed surface tells us how much electric flux is coming out of the surface, and since positive charge is a source of electric flux, the integral of d dot ds tells us how much charge is enclosed. Now we're going to apply Gauss's law here to a small differential volume element to determine the operation of divergence and find the point or differential form of Gauss's law. Here we have a small cube of sides delta x, delta y, and delta z. So the volume of this cube, delta v, is delta x, delta y, delta z. Okay, so now we're going to apply Gauss's law to this small cube. So the integral of d dot ds over the surface of the cube, so the surface of delta v, is going to equal the charge enclosed in that cube, and I will designate that as q sub delta v. Okay, so now the next step is we're going to divide both sides of this equation by delta v, and then take the limit as delta v goes to 0. So this operation on the left-hand side is what is known as the divergence of d. And this is also written as del dot d, and in part 2 I will explain this nomenclature of what del dot d represents. Now, looking on the right-hand side of this equation, we have a charge over a volume, coulombs per meter cubed. So as the limit of delta v goes to 0, this is just the charge density at a point. That's just our volume charge density, rho sub v. Okay, so the divergence of d is equal to the charge density. So the divergence of d equaling the volume charge density is the point or differential form of Gauss's law. And now we have a physical feeling for what this operation of divergence is doing. If we have this electric flux density field, we see that in this region we have a source of electric flux, so there must be positive charge in this region. And in this region we have a sink of electric flux, so there must be negative charge in this region. So let's think of the divergence of this field at various points. So let's say we want to look at the divergence at some point here. Okay, so the way to think of that is go back to thinking about this small differential volume around that point. And remember that the divergence is the integral of d dot ds over that surface of that small volume divided by the volume and the limit as the volume goes to 0. Okay, so the denominator here is always going to be positive even though it's getting smaller and smaller. And if we look at the numerator, the integral of d dot ds tells us how much flux is leaving this volume, but whatever flux enters also is leaving, so the integral of d dot ds around this surface is going to be 0. So at that point, the divergence is 0, which is telling us there's no charge density at that point. Okay, so let's look at a point here. Okay, again, think of a small volume around that point. And you're going to integrate d dot ds around that small volume, divide by the volume, and take the limit as delta v goes to 0. Well, everywhere on the surface here, flux is leaving the volume, so the integral of d dot ds around that volume is going to be positive. So the divergence at that point is going to be greater than 0. So the charge density is greater than 0 at that point. So the positive divergence tells us there's positive charge at that point. So finally, let's look at this point right here. Again, think of a small volume around that point. The integral of d dot ds on the surface of this small volume is going to be negative because all the flux everywhere enters the volume, so the integral of d dot ds is going to be negative around the surface. So at this point, the divergence of d is less than 0, so the charge density at that point is less than 0. We now have a conceptual understanding for this operation of divergence of a vector field, and specifically the case for Gauss's law and the connection between electric charge and electric flux. Now there remains the mechanics of, if you have a vector field, how do you actually find the divergence of the vector field? And we will look at doing that in Cartesian coordinates in part 2.